everybody. Let's look at cyclic groups. In section 1.3, my claim is cyclic groups should be your favorite kind of group. We can classify them. There's something familiar to you. All finitely generated abelian groups, as we'll see later, are made out of cyclic groups. So what it amounts to is when you think group, cyclic groups are probably the most tangible. Even the symmetry groups that we've already encountered, it's a little bit hard maybe to put our hands exactly on the structure of a symmetry group. But the structures of cyclic groups, pretty easy. A preliminary result, which really explains all of that. It tells you exactly what cyclic groups look like. They come in two flavors, finite and infinite. Theorem 1.3.1 says, every subgroup H of the additive group Z is cyclic. Either H is the trivial group, the group generated simply by 0, and therefore the group consisting only of 0, or H is generated by some number m, where some integer m, where m is the least positive integer in that group. Other than the trivial group, all these other groups are infinite. I guess that's actually not the classification we want, but we'll use that in the proof of the classification, which will be Theorem 1.3.2, sorry. But let's go through and deal with the structure of the integers as an additive group. Okay. So proof of this, not terribly involved. Either what we've got here, H equals the trivial group, or H contains a least positive integer m. The formal definition of the natural numbers, the positive integers, arguably the non-negative integers, is that every set of natural numbers has a least element. It's called the law of well ordering of the natural numbers. See page 10 for some details on that, but this is familiar stuff to you. So we must have a least positive integer in this group. Call that least positive integer m. H is closed under the binary operation. The binary operation is addition here, by the way. So the group generated by m would simply be all integer multiples of m. Granted, multiplication is not a thing that you do in an additive group, but I'm appealing to your knowledge of the integers on this. So what we get is m, m plus m, m plus m plus m, the additive inverse of m, the additive inverse of m plus m, all right, negative 2m if you like. The meaning of taking an integer multiple, say, in an additive group, or as an exponent, if we were to use multiplicative notation. So we get all, if you will, integer multiples of m in the group generated by m. We said H is a non-trivial group, so we know it contains a least positive integer m, and such H must contain the subgroup generated by that element m. In other words, just comes from the, the closure of the binary operation. We're trying to show H equals the group generated by m when we're not dealing with a trivial subgroup. So we need to reverse this inequality. So let lowercase h be an element of group capital H. Then lowercase h would be an integer that would be of the form qm plus r, where q and r are integers, and r itself is between 0 and m, excluding m, possibly including 0, by the division algorithm. Okay, so we've got h as an additive subgroup of the integers, so I know h itself is an integer, so this is just a conversation really about properties of integers, which seems rather specialized, but as we'll see, integers are intimately related to cyclic groups. So division algorithm says we can take h divided by m, goes in q times, q for quotient, and we have a remainder of r. Usual division algorithm. See Theorem 0.6.3 for more details on that. So we can write H in this form. The important thing is that R is between 0 and M and is strictly less than M. We can rearrange this, solving for R, just doing arithmetic with integers. R equals H minus QM. That must be an element of H, be group capital H, because we know lowercase h is in capital H, and we know all multiples of M are in H, so this multiple negative Q of M is also in H. So closure under the binary operation of addition again. So R itself must be in H, closure. Now M was chose to be the minimal positive integer in group H. So if we've got R also in group H, and we've got R between 0 and M, well, R can't be strictly less than M and be in the group unless it equals 0 itself, because M is the smallest positive integer in the group by choice. So we must have the situation where this R equals 0, so up here, R equals 0, and H must be QM plus 0, if you will. So H is just a multiple of M. Oh, but that means if H is simply some integer multiple of M, then H must be in the group generated by M, the subgroup of the integers generated by M itself. This lowercase h was an arbitrary element of capital H, so all of group H must be a subset of the group generated by M. We have group generated by M as a subset of H is a subset of the group generated by M, so there's the equality. So it must be that H equals the group generated by M. The only other claim was if H is not the trivial group, then H is infinite. So if H is not the trivial group, take any two integers different, any two distinct integers. K1 times M doesn't equal K2 times M. This is valid for any integers. So there's your way to generate an infinite number of multiples of M. And so we get an infinite group out of this. So returning to the notes. So some properties of the additive group of integers, it's cyclic, and we see ways to generate some subgroups of the integers. The subgroups are now classified by this result. We've said the group generated by M, it's all integer multiples of M. It's commonly denoted simply MZ. When we look at Z sub M in a quotient group setting down the road, this will play a big role. Here we're taking M to be any natural number or 0. A little comment about this. Depending on which book you use, the natural numbers may, symbol in natural numbers, may indicate the positive integers, or it may indicate the non-negative integers. It's not universally agreed whether 0 is a natural number or not. In the analysis setting, it's common to use the natural numbers as the positive integers. If we take that approach, we'll have to throw 0 in. Hungerford actually counts 0 as a natural number. So I'll be unambiguous. You can't lose with this. Certainly 0 is included in that set, along with all the positive integers. So now we're in a position to classify cyclic groups and further justify my claim. You like cyclic groups. You like them because they're really tangible. In fact, they're closely related to the integers, and the integers mod M as follows. Theorem 1.3.2 says, every infinite cyclic group is isomorphic to the additive group of integers, and every finite cyclic group of order M is isomorphic to the additive group integers mod M. So that's why I say you like cyclic groups. They're tangible. You certainly are familiar with the integers and the integers mod M. So let's look at a proof of that. 1.3.2. Okay, first, suppose G is a cyclic group. Let G be generated by the single element A. Define alpha as a mapping from the integers into the group as alpha of integer K equals A to the integer k power. If you'll let me read it like that, using multiplicative notation for this group G. This is a homomorphism by theorem 1.1.9. In fact, we'll see under appropriate conditions, we got an isomorphism. Let's take a quick look at theorem 1.1.9. So what we'd be claiming is preservation of binary operations. That's what homomorphisms are. Not necessarily one-to-one and onto. Theorem 1.1.9, it just happened to have sitting around here, said, so it's probably this first one that matters. Here we've got m and n as integers, and A is an element of a group. So this is the same setting that we have in our current conversation. And we're saying a to the m times a to the n equals a to the m plus n. Follows just from what we notationally mean by having exponents on group elements in a multiplicative group in this case. And this is exactly what we were looking at. This is the homomorphism. Let's say here we got the homomorphism applied to m plus n, produces this. Apply the homomorphism to m, produces a to the m. Apply the homomorphism to n, produces a to the n. In the integers, the group operation is addition. So there's the addition right there that establishes that, in fact, this mapping as given here is a homomorphism. So straightforward stuff, a few details may be omitted, but it's all covered in theorem 1.1.9. If A is a generator of G, then the claim is alpha is onto. It's surjective, and alpha is an epimorphism. Not much of a surprise. We're letting theorem 1.2.8 carry the weight on this. The reason is, we'll look at that theorem here in a sec. The reason is, hey, if A is a generator of G, I know what all the elements of G look like. They're, well, integer powers of element A. That's what theorem 1.2.8 says. Theorem 1.2.8 says, if we have a cyclic group, this is the part that matters. If we have group G generated by element A, then the elements of G are the integer powers of A. So our mapping will produce all integer powers of A. And so we'll have an surjective mapping, an onto mapping. That is, alpha is an epimorphism. So homomorphism, onto, surjective. Is it one-to-one? Is it injective? Well, maybe, maybe not. Here we're saying infinite cyclic groups are isomorphic to the integers, and finite cyclic groups are isomorphic to the integers mod m for some m. So we get a little bifurcation in the argument here. Let's look at the kernel of alpha. If the kernel of alpha consists only of 0, then alpha is one-to-one, alpha is injective. Theorem 1.2.3 part 1 says exactly that. So if we want to check one-to-oneness, injectivity, then we can look at the kernel. If the kernel consists only of the identity in whatever group we have here, it's the group of integers. Alpha maps the integers into G. So if the kernel consists only of the identity in this group, which is 0, then we have a one-to-one mapping, an injective mapping. So if that's the case, then this epimorphism is in fact an isomorphism, one-to-one onto homomorphism, or if you like, injective, surjective homomorphism, or if you like, bijective homomorphism. So there's all the lingo that goes with this stuff. But anyhow, if the kernel consists only of the identity here, then we got ourselves an isomorphism, and that isomorphism maps Z to the group of the integers to group G. And so we've got the integers are isomorphic to G. And the claim was we either get isomorphic to G or isomorphic to these little subgroups. So if the kernel of alpha consists only of 0, then G is isomorphic to the integers. If the kernel doesn't equal simply the identity. Of course, it includes the identity, but if it includes some other stuff, then we'll show that the group is isomorphic to integers mod n. If kernel of alpha is not equal simply to 0, we know the kernel of alpha is a non-trivial subgroup of the integers. It's actually exercise 1.2.9 is to show that the kernel of a homomorphism forms a subgroup of the domain of that homomorphism. Exercise 9 in the previous section, probably you did this in senior level algebra as well, straightforward manipulations of the definition of subgroup and kernel to establish that. But we know the kernel must be a non-trivial subgroup, non-trivial because we're assuming it's not simply 0, of the integers. Okay, so we got ourselves a set of integers. Do you know what subgroups of the integers look like? Yeah, we just did that in Theorem 1.3.1. Subgroup of the integers is of the form cyclic group generated by m, where m is the least positive integer in that subgroup. That we showed in the first result. So we've got the kernel given by this particular cyclic subgroup. We want to show that G itself is isomorphic to the integers mod m. So m's made its appearance in the proof. We want to show Z sub m is isomorphic to G. All right. For a couple of integers, r and s, a to the r equals a to the s, if and only if a to the r minus s equals the identity, or the identity in the integers is 0. Now, we had a mapping that would take r minus s, this homomorphism, would take r minus s to a to the r minus s power. Our mapping alpha did that. So this holds if and only if r minus s then is in the kernel of alpha. It's taken us to the identity, because it's taken us to the identity in G, the image is in G. So we've got r minus s, then being in the cyclic group generated by m, we saw the kernel was of that form before. Well, r minus s is in the cyclic group generated by m, just all all integer multiples of m. That occurs if and only if r minus s is some multiple of m. That is, if m divides r minus s. And m divides r minus s if and only if the equivalence class containing r is the same as the equivalence class containing s in Z sub m. Remember, we use this bar to indicate equivalence classes or congruence classes in Z sub m in this setting. So r minus s divisible by m tells you r and s differ by a multiple of m. R and s are congruent modulo m, or this statement in terms of equivalence classes. So let's define beta mapping Z sub m into G, right? We need to shift the conversation from the integers to the integers mod m. So now we need to map equivalence classes instead of integers themselves. But we'll take the mapping beta that takes equivalence class k bar and maps it to a to the k power in group G. This is well defined. Yeah, that's what we just showed. What we've got here is if here we go, if r bar equals s bar in Z sub m, then these are if and only if statements. If I've got equality here, r bar equals s bar, going backwards, we've got a to the r equals a to the s. So if I take different representatives of k bar, beta will map those equivalence classes still to the same element of G. For example, if r bar equals s bar equals k bar, if I use representatives r and s in this mapping, we get a to the r and we get a to the s when I apply beta to r bar or s bar the mapping's defined in terms of a representative. So that's when I need to address the well-defined stuff. And we've checked to see, different representatives R and S from the same equivalence class produce the same result here. So beta deals with that type of mapping. First off, beta is well-defined. Beta is a homomorphism. Next, straightforward, beta of R bar plus S bar allows me to immediately talk about group manipulations. That would be A to the R plus S. We're taking a representative R bar plus a representative of S bar, or if you like, a representative of R plus S bar. Take R plus S. We know what these symbols mean. It was at Theorem 1.1.9 that said A to the R plus S is the same as A to the R times A to the S. Multiplicative notation. Hey, A to the R is beta of R bar, right? And A to the S is beta of S bar. So we've got beta of R bar plus S bar equals beta of R bar times beta of S bar. That's a homomorphism, right? We've got a mapping from Z sub m into G. Z sub m is an additive group. There's your binary operation of addition of equivalence classes right there. And G, we're using multiplicative notation in group G, and there's your binary operation right between those two. So we are preserving binary operations, even though one group uses additive notation and the other one uses multiplicative notation. It's just notation. So this beta mapping, in fact, is a homomorphism. A is a generator of G, so this homomorphism is an onto homomorphism. That is, it's an epimorphism, onto or surjective. So we've got an onto homomorphism. If we'll look at the mapping, the kernel, we also want to show this mapping's one-to-one. We want to show the mapping from Z sub m to G, in this case, is an isomorphism. So to the kernel, beta of K bar equals the identity if and only if A to the K is the identity. The identity is A to the 0 in terms of that generator A of group G. And this happens if and only if K bar equals 0 bar in Z sub m. That's the kind of thing we've established up here. So we get K bar, 0 bar, same equivalence class. And maybe we took different representatives, but we get those by the above argument to be in the same equivalence class. So the kernel of beta does consist only of the identity. All right, it's only the identity in Z sub m. And the identity in Z sub m is the equivalence class containing 0, this 0 bar. It's only one thing. All right, it's an equivalence class. That's one thing in the integers mod m. In the integers, it's a whole bunch of stuff. It's all multiples of m, all integer multiples of m. But we're not dealing with the integers this time. We're dealing with the integers mod m. The integers have as elements integers. Integers mod m, Z sub m, has as its elements equivalence classes. There's sets of integers, not integers themselves. So it's a little subtle when you first encounter it. In terms of what Z sub m really is, but it contains equivalence classes. So we've got the kernel of beta to consist only of the identity, 0 bar, in this group, Z sub m. That tells you got yourself an injective or one-to-one mapping. So we've got one-to-one onto homomorphism. This beta mapping integers mod m to G, it's an isomorphism. And so Z sub m is isomorphic to G, and that was the other claim. So infinite cyclic groups, isomorphic to the integers. Finite cyclic groups, isomorphic to Z sub m. We took G as a group. When it was infinite, it was isomorphic to Z. When it was finite, it was isomorphic to Z sub m, as claimed. So one more time, I say, back to section 3.1, that's why you like cyclic groups. We're talking cyclic groups. We're effectively talking either the integers or the integers mod m for some m. And we'll take advantage of that in some of the proofs to follow. Definition of the order of an element of a group. Let G be a group and A an element of group G. The order of element A is the order of the cyclic subgroup generated by A, denoted with kind of absolute value looking things, just like we used when we talked about the order of a group. So we've got order of a group defined. We have in here so far just distinguished between finite and infinite groups. And now we have the order of an element, defined in terms of the order of the cyclic subgroup which it generates. But different stuff, order of an element versus order of a group. All right, let's look at some properties of elements of finite and infinite order. Theorem 1.3.4 states a whole bunch of things. I want to go through a proof just of the last one, really. Let G be a group and A an element of group G. A couple of properties in the event that A has infinite order. If element A has infinite order, then A to the K equals the identity if and only if K equals 0. Of course, if K equals 0, A to the K equals the identity. That's the meaning of A to the 0 power, right? That's notation, really. K not equal to 0 really is a claim that's made here in the event that A is infinite order. So the only time we get the identity out in an infinite order element is when we take the exponent to be 0. The elements of A to the K are distinct for all values of K as it ranges over the integers. You might see how those are rather closely related also. And think integers. You're perfectly justified in thinking integers when I say infinite cyclic group, or multiples of the integers, which is isomorphic to the integers. Up to isomorphism, you're good thinking integers. If A is an element of finite order M. Okay, so now we're talking about a group generated by A of order M. Well, you know by the previous result, you're good to be thinking integers mod M. So the following should sound familiar as properties of the integers mod M. The elements of which are equivalence classes, remember. M, the order of element A, is the least positive integer such that A to the M equals the identity. All right, least positive integer, of course, A to the 0 equals the identity. We just talked about that. The least positive integer for which A to the M equals the identity equals the order of that element as well. I bet you if we take powers of A between 0 and M minus 1, we get distinct elements. We must. I mean, that's an implication of this, and that's consistent with this little comment we had above in part 2 in the infinite order case. This is actually fairly useful. In finding the order of an element, it might be useful to keep this in mind. It's the smallest positive exponent I put on the element in multiplicative notation that gives us out the identity. Next, still in the realm that element A is of finite order M. If A to the K equals the A to the K equals the identity if and only if M divides K, or in other words, K is a multiple of M. And that makes sense. Think integers mod M. So that's not a surprising result either. A to the R equals A to the S if and only if R and S as integers are congruent modulo M. Well, that makes sense. R minus S is a multiple of M, in other words, and we saw something like that in the previous argument. Here we explicitly say the group generated by A when A is an element of order M consists of the distinct elements A squared, A cubed, A to the M minus 1, A to the M, but A to the M is going to equal 0 because M is the order if you believe part 3. So these are intimately tied together. There's exactly what the elements of that group generated by an element of order M are. The identity A squared up to A to the M minus 1, if you like. And let's prove this last one. It's a 2 or 3 line proof. It says for each K, such that K divides M, A to the K, order of, is M over K. Okay, so we're taking a divisor of M, the order of element A, taking A to that divisor power, giving us an element of group G, was it? And considering the order of that element A to the K and claiming that's M divided by K. Maybe not immediately obvious unless you think about this in terms of integers mod M, which you're perfectly justified in doing because this group generated by A of order M, it's isomorphic to the integers mod M. So let's look at a proof of part 7. First, we have A to the K to the M divided by K. Remember, we got into this mess saying K does in fact divide M. So M divided by K itself is an integer. Properties of multiplication of powers. Theorem 1.1.9 dealt with this. It says multiply exponents. The K's cancel. We get A to the M. And you know A to the M equals the identity. A to the M equals the identity, part 3. So assume A to the K to the R also equals the identity, but take R to be strictly less than M over K. Raising A to the K to the M over K power generated the identity. Suppose A to the K to some smaller power, lesser power, also generates the identity, where that exponent is between 0 and M over K. So I'm not allowing it to be 0. Of course, if I let R equal 0, then this is going to be true. Suppose we find a smaller positive, right? Remember part 3 up here. We find a smaller positive exponent on this element A to the K that produces the identity. Then we've got A to the K over R equals the identity, you know, multiply exponents, Theorem 1.1.9, part 2, I suppose. K times R is less than K times M over K because R was chosen to be less than M over K. So this inequality justifies this inequality. K's cancel here, we get an M out. We've found a power, KR, which is strictly less than M, to which we raise element A to A to the KR, there it is, A to the KR, and get the identity out. There can't be a lesser exponent which produces the identity in that sense. That contradicts part 3. M is the least positive integer such that A to the M equals the identity. So that contradicts there being a smaller positive value for which that works, not a smaller value. Then the smallest value must be this M over K, and that must be the order of element A to the K by this part 3. Think integers mod M, and you're good to go for something a touch more intuitive. All right, a couple more results. Theorem 1.3.5 says every homomorphic image and every subgroup of a cyclic group is cyclic. Like that, every subgroup of a cyclic group is cyclic. Wonder what generates those subgroups. That we'll address in the next result. In particular, if H is a non-trivial subgroup of group G, cyclic and generated by A, and M is a least positive integer such that A to the M is in H, then, well, this classifies it right here as well. H is the cyclic group generated by A to the M. So homomorphic images of cyclic groups are cyclic. I think that'll be pretty straightforward. And subgroups of cyclic groups are cyclic, and this is a way to generate those subgroups. Down below, we'll give generators if and only if. So this is more specialized in what the subgroups look like. So let's look at 1.3.5. Excuse me. Making claims that, first off, homomorphic images of cyclic groups are cyclic. All right. Let F, map G to K, be a group homomorphism where group G is generated by element A, as we claimed upstairs. For any A to the K in G, we have F of A to the K is F of A to the K. On the left, this repeated multiplication is done in group G. On the right, it's done in group K, by the way. So the image of F is the group generated by F of A. We got a group homomorphism. What happens here in terms of what you get out of that homomorphism? Well, the things that go in are elements of G, and elements of G are all of the form A to the K, where K is an integer. And what comes out is F of A to the K. And that's the only kind of thing that comes out, because this is the only kind of thing you can put in. So the image of F is all powers of F of A, where A is a generator of group G. So the image of F is simply the group generated by F of A, and there's your homomorphic image of cyclic groups as cyclic claim. So there's the first claim. Next, let's talk about subgroups. Suppose H is a subgroup of G. All right, we want to show that H is itself cyclic and it's generated by A to the M, where M is the least positive integer, such that A to the M is in H. Sounds a bunch like a conversation we'd have if we were describing integers mod M. And it is, except the integers always appear in these exponents. You know, that was a homomorphism we had back when we were looking at showing ultimately an isomorphism between Z sub M and groups, finite cyclic groups. So now suppose H is a subgroup of G, let M be the least positive integer such that A to the M is an element of H. Well, A to the M is in H, so if we take all integer multiples of A to the M, integer powers, I guess, of A to the M, then we certainly get something in H. That's just closure of H as a subgroup under the binary operation. So if this element is in there, then all powers of this element are in there, simply making that claim. We're trying to show H equals the group generated by A to the M. Certainly the group generated by A to the M is a subset of H. We just need to reverse this subset inequality. So we need to take an arbitrary element of group H and show that is A to the M to some power. So take H, lowercase h, to be in subgroup capital H, a subgroup of G. Then we know H is some power of A because group G is generated by element A. H is a subgroup of that, so any element of H, also an element of G, is some power of A. Let's take that exponent and factor it in a certain way. We're dividing it by M is what we're doing. So we're going to take that exponent, divide it by M, getting a quotient Q and a remainder R. So whatever exponent you have to put on A to get H, there is such a thing, since H is in G and G is generated by A. Take that exponent, divide it by Q, divide it by M. M goes in Q times with a remainder R. What we're using is a division algorithm here, Theorem 0.6.3. These exponents, they're going to be integers. So that gets us in some familiar territory. Q is an integer, R is an integer, not just any integer on the R. R is between 0 and M, strictly less than M, and possibly the remainder is 0. In fact, we'll show it as 0 in this case. But you can take any integer and write it in this form, Qm plus R for given M. Our M was given back up here when we picked it, according to that protocol. Now, we know A to the M is in H. So we know A to the M to the Q power is in H. Remember, all powers of A to the M are in H. If A to the QM is in H, then its inverse is in H because H is a group. So A to the negative QM is in H. So here's what we've got. A to the QM plus R, that's an element of subgroup H. A to the QM inverse is also in H. So we can take that H, multiply it by this thing, an element of subgroup H, the A to the negative QM. H itself was of this form. Add exponents. We get A to the R. So A to the R must be in H. But wait, m was the least positive integer for which a to the m was an h. R was between 0 and m. It can't be positive because m was the least positive exponent of a that gave us an element of h. That's how m was chosen. So it must be that r equals 0. So some similar arguments in these proofs. It must be that r equals 0. That is, h equals a to the qm plus r is in h. Then r must equal 0. And h equals a to the qm, where q is an integer. In other words, h is some power, the exponent's q, of a to the m. So we took an arbitrary element lowercase h of group capital H and showed it's a power of a to the m. Remember what we're trying to show here? Trying to reverse this set inequality. We're trying to show h, and we chose an arbitrary element of capital H is an element of a to the m. That is, subgroup capital H is a subset of this group generated by a to the m. Here we've got capital H is a subset of this group. This group is a subset of H. So we can draw the conclusion that of equality, group capital H is equal to the group generated by a to the m, and that was the claim. So this subgroups of cyclic groups is cyclic. That's a very useful thing. And this goes beyond that, and it tells you how to find a generator of the subgroups to boot. How to find a generator. There might be other generators as well, and that's what the final result in this section deals with. The following classifies generators of cyclic groups. So let G be a cyclic group generated by element A. If G is infinite, the claim is A and A inverse are the only generators of G. If G is finite of order m, then A to the k is a generator of G if and only if k and m are relatively prime. This notation out of chapter 0 represents greatest common divisor of k and m. So the greatest common divisor of k and m is 1. That is, k and m are relatively prime. It's also called coprime sometimes. This makes sense. We ought to be able to get some intuition out of this. Because I know what first off, I know what an infinite cyclic group looks like. It's isomorphic to the integers. What generates the integers? Remember, they're an additive group. 1 and -1 under addition generates the integers. If I treat the integers as a cyclic group, then I can take either 1 as a generator. Certainly that generates everything. Or I can take -1, that generates 1, and so it generates everything. Were I to take something other than 1 in the integers to try to get to generate the integers themselves, it won't work. Take 2, all you get's even numbers then, so it doesn't work. Take 3, all you get's multiples of 3, it doesn't work. And that's part of the proof in this, but that does make perfect sense. Down here, this should make some pretty good sense as well. If I were looking for generators of, say, Z6, what generates Z6? 0 bar doesn't generate anything but a trivial group. Z1 does. Z2 doesn't. In Z6, 2 bar will generate 2 bar, 4 bar, and 0 bar. Generates a group of order 3, not a group of order 6. 4 bar, skip 3 bar. 3 bar generates 3 bar and 0 bar, subgroup of order 2. 4 bar generates 4 bar, 2 bar, and 0 bar. It's a group of order 3 again. 5 bar generates 5 bar, 10, which is 4 bar, 9, which is 3 bar, 8, which is 2 bar. What are we doing? 5, add 5 to that, and I get 1 bar, and then I get 0 bar. Yeah, 5 bar generates everything. 5 bar is kind of the -1 in the world of Z sub 6. So these things make sense. Consider a small example, and this isn't the least bit a surprising result. Let's go through proof. We're going to be talking to integers a lot in this. You know, when we're talking infinite cyclic groups or finite cyclic groups, we may as well be talking integers and integers mod n. We've shown that those things are isomorphic. So let G be infinite. G is isomorphic to the integers, so let's show this result for the integers and that up to isomorphism. Shows this result for group G itself. Certainly the integers are generated by 1 and -1. If we choose something other than 1 and -1, and 0, if I choose 0, I get nothing generated, the trivial group. Consider the group generated by M, when M is something other than those three things. The absolute value of M is the smallest positive integer in this group, so it doesn't include 1. So something goes wrong if you don't take 1 or -1 as a generator. You miss element 1 in the group which you generate, for example. So you get a proper subgroup of the integers, but you're not getting the integers themselves. So the only generators of the integers are 1 and -1. In group G, equivalently, the only generators are A and A inverse. If you like, A to the 1 and A to the -1. Dealing with that isomorphism we introduced upstairs, beta, I think we called it, between, alpha, I think we called it, between a group and the integers. So we made the integers exponents. So equivalently, these are the generators of this group G. All right, so that takes care of if G is infinite. The only generators we get are A and A inverse, where G itself is generated by A. If G is finite and of order M, all right, let G be finite, order n, we know it's isomorphic to Z sub m, so we may as well have a conversation about Z sub m, same way we worked the previous one. G is isomorphic to integers mod m. M is the order of group G. If K and M are relatively prime, then, okay, I need a little result out of chapter 0, an elementary set theory result. If we take relatively prime integers, K and M, then there are integers C and D such that CK plus DM equals 1. There's that greatest common divisor. Probably this can be generalized. But we'll take that as given. See theorem 0.6.5 for details. I don't think there's proofs of these number theory results in the Hungerford book, but we'll take this as given from previous experience. Here's a multiple of n. Okay, we want to talk not integers, but integers mod m. And there's a multiple of m right there. What we have here then is C times K and 1 differ by an integer multiple of m. So C times K is congruent to 1 mod m. In terms of equivalence classes, that is, C copies of K bar, the equivalence class containing K, equals the equivalence class containing 1. So we've taken C copies of K bar. How do you add those things together? With representative Y's. So we'll get K plus K plus K plus K C times bar, equivalence class containing that, equals 1 bar. So that's just an equivalence class way of saying C times K is congruent to 1 modulo M. So if we take any element of the integers mod M, then if we'll take n copies of C copies of K, and I'm kind of trying to multiply both sides of this by n. On the right-hand side, I want 1 bar plus 1 bar plus 1 bar n times. On the left side, I want this stuff n times. That gives us a total of n times C copies of K bar, right? N copies of this and n copies of that produces this equation. So we took an arbitrary equivalence class in Z sub m, and we generated it with these K bars. So K bar generates Z sub m. All right. We've got a generator of Z sub m, we want to talk about a restriction on the number of generators. Here we assume K was relatively prime to M and showed it generates Z sub M. Now we want to show, if and only if somewhere in there, if K and M are not relatively prime, then we don't get a generator. So suppose K and M, greatest common divisor is R, something greater than 1. So they're not relatively prime. Consider N, an integer, is M divided by R. We know that R is a divisor of M and of K for that matter. So take N to be M divided by R. That's strictly less than M because R is strictly greater than 1. Good old-fashioned arithmetic. Then if we'll take N copies of K bar, that'll produce, by adding by representatives, that'll produce the equivalence class containing NK. We just saw N is M divided by R, so replace the N with M divided by R, keep the K. We can rewrite that as K divided by R times M. K divided by R is also an integer, right? R divides K, so greatest common divisor of these two. So by the definition of how you add equivalence classes, we can treat that as K divided by R times M bar, equivalence class containing M. So we're taking copies of M bar, and from this, we get 0 bar. Momentarily stunned, we get 0 bar. Because we're working modulo M. Okay, so M bar is 0 bar. We're in Z sub M. So the equivalence class containing M is the equivalence class containing 0 bar. We get K over R copies of M bar or K over R copies of 0 bar. So we get 0 bar out from the arithmetic there. And K bar doesn't generate Z sub M. What we're getting is it's generating some subgroup. It hit 0 too early. We took N times K bar, N being something strictly less than M, and the equivalence class containing N was never generated. We reached 0 too soon. So what we're getting then is a subgroup of order at most, M over R out of this. It's not generating all of Z sub M. That is, K bar is a generator of Z sub M if and only if the greatest common divisor of K and M equals 1. That was a conversation held in the context of integers mod M. Let's change it back to finite cyclic groups. A to the K is a generator of the finite group G generated by A if and only if that exponent and the order of this group are relatively prime. M was the order of this finite cyclic group. G is given there. So that simply takes this argument from Z sub M and describes it in terms of a group G generated by element A. And, well, that takes care of cyclic groups. I say again, you like cyclic groups because they're so tangible, and you should be pretty comfortable with the integers, any integers mod M. Next, we'll look at cosets and counting, I think is the title of the next section. After that, we'll take off into terms of normal subgroups and quotient groups. So things pick up a little bit starting in the next section and a good deal in the section following that, though it's still review material from your senior level algebra class. I'll see you in section 1.4 after a while. Have a nice day.